for anyone else.
Yeah.
Stel je voor dat je de jeugd bent. Dat je het vanuit een ander perspectief kon bekijken. Is het duidelijk dat ik al rondkijken, denk ik.
Okay, good morning everyone.
Good morning.
I hope that you had a good weekend. Always a pleasure to have a lecture on the Monday morning to start the week. Before I start, I just want to come back on what we said last week about the group projects. So I already had some discussion about some groups. Don't hesitate to come to my office or send me an email if you have any question, because I know that all the lectures we are going to see theme by theme. So maybe we are going to see something in the future that you want information right now. I had a very positive feedback from some students. I had some stuff from the next sessions directly on Canvas, so you already have the literature, for instance. And if you want anything else that you see in the course program that we will do later, just ask me, and I will try my best to give you advices. Because of course, if for instance you want to have more information about recycling, for instance, it's going to be one of the last lecture, so you cannot really wait until January to start to work on that. It's not possible. So I will try my best to have as much as possible on Canvas, and you can have information. Next week we are going to have the group meeting, so we are going to discuss that in the second part of this course. We should add today the information about the slides that you have to make for next week, and something I already said to some students, it's completely up to you. I mean, we are doing that to help you. It's to give you a positive feedback or negative feedback if you are not going in the right direction. So you can come and do nothing. It's going to be your problem at the end, because it's really for you that we are doing that, to help you to be sure that you are working on the right thing. But that's why I'm going to indicate to you what exactly you have to prepare, a couple of slides in which theme that we can have a look to in 30 minutes to have a discussion with all of you, but we are going to discuss that later. So today we are going to talk about polymer and plastic material, and for me, when I was designing this course, in general, I really wanted to add something about plastic for two reasons. The first one is that I have a lot of experience with that, especially with the bioplastics. I used to work with it a lot during my PhD, so for me it's a really cool topic to show to master students, because we can do a lot of things with plastic material. And it leads to the second thing. Most of the time, I noticed that master students from different backgrounds has almost no knowledge about plastic material. It's not your fault. It's just that usually plastic goes with chemistry, and it's engineering, chemical engineering students that have more experience with plastic material. And when we are talking about civil engineering, building engineering, we are a little bit like excluding the plastic, and I do think that it's quite important topic, and we will see that actually, yeah, plastic and construction building material are really connected. Even though it's less than concrete or steel or whatever, but it leads to a lot of very, very informative stuff that I will try to show you today. So what we are going to see today, what are going to be the learning outcome, learning objective of the course today. First of all, I mean, always the same, it's the fourth lecture that we have together. We are going to discuss the property of the plastic. So the first part of the course are really going to be a lot of information about plastic material, or we can compare them, and especially what are the properties. So for instance, if I compare plastic and metal, of course you can tell me this is plastic, this is a metal, but why? What are the big differences in terms of technical performances and property in general? And then, because you have millions of plastic material out there, we are going to try to compare them between each other. So discussing the microstructure and the property, so it's always the same as something we already have seen in the previous lecture. So going to identify the different material and then to compare them between them, trying to evaluate, for instance, from the microstructure, what are going to be the difference in terms of property and technical performances. And then we are going to try to, I'm going to try to give you as much information as possible that in the future, for instance, during the final exam, you actually can explain me, defend your idea about what are the benefits and the drawback of using plastics as a construction building material. It's a very, very cool material. You can do a lot of things with it, but it leads also to a lot of problems. I'm going to try to put the emphasis today on the problematics, because of course, if plastic was so good, we would only use plastic everywhere because it's super cheap. This is a big advantage. And as I said, in application, when it's cheap, usually we have the tendency to use it. So we also have problems, that's why we are not using plastic all the time, and we are going to explain that, especially in the second part of the lecture, when we are going to talk about application. So this is going to be, this course is going to be divided today. I'm going to show you in the first part of the course, it's really going to be, maybe it's going to be a bit boring for the Monday morning, but I need to give you as much information as possible about polymers. These slides are also for you. I mean, you can use it later. You will have a lot of information, sometimes even too much, but it's good for you that you can use it for instance, your project if you want information about it. We are going to talk about polymer property, microstructure, and processing, so we can make and shape plastics. We're going to make a break, and then we are going to discuss applications and applied sciences. So all the polymer actually degrades, the durability of this material, what are the different applications, so a lot of pictures to finish that. And we are going to end with the pollution and recycling of polymer, which is to me a very, very important problem of polymer, and it's something we have to discuss together because I think it's a problem, not even, it's a society problem, so we have to discuss that anyway. Let's start with the definition itself of a polymer. What actually is a polymer? Because we are saying plastic, but plastic is not actually the real word. We should not use plastic. The real word is polymer. And, well, the definition is here, but how you can explain in your own word, for instance, what's a plastic material? If I have, for instance, to ask you, okay, this is plastic. Why it's plastic? Or you can explain me that it's plastic. Or you can convince me that this is plastic. It's not easy, right?
It's an organic macromolecule composed of many repeated small proteins.
If you read the slide, yes, it helps. It helps. But how do you understand that actually? Is it making sense to you when you are reading such a complex sentence? Because this is really the scientific definition. But if we can go in detail, so first organic. So as compared to inorganic, so inorganic is everything which is, for instance, steel, concrete, so not made of carbon and hydrogen. So this is an organic. So this is made of carbon, hydrogen, and this is the first thing. So we can differ like from the mineral material. Then it's a macromolecule. So macromolecule is a very, very long molecule. And the definition is here. For instance, this is the ethylene. It's a very conventional organic molecule. So sorry to, again, doing a chemistry lecture here. It's going to be one of the only slides, I hope. And when you have only this molecule, you have just a molecule, a normal one, very close, for instance, as the size of water, for instance. And then you see here you have a small n, which is very important for the polymer, is this unit, the smallest part of the molecule. We are going to repeat it like n times. So when n is over 10, you have what you call an oligomer. So oligomer is just a long molecule, and you have the repeating unit, like for instance 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It has different property because when you are increasing the size of the chain, of course you are modifying a lot of property. When it's short, for instance, or this organic material, the shorter it becomes gas. So that's why, for instance, all the petroleum source, the gas that you are using for your car is pretty short, but not too short material chain. And then you are increasing the length of the chain, and when you continue to increasing the length of the chain, when n becomes greater than 100, 1,000, 10,000, 100,000, you have what we call a polymer, because these repetitive units, we are repeating it like n number of times. It's completely random. In one polymer, sometimes you have 10,000, when 1 million in the same batch. It's going to be a distribution curve. like that, or you will have a big average. And this is what we call polymer. So actually, in my mouse here, I have a very, very complex and long chains that are all mixed together and making this specific material. And then, so macromolecule composed of many repeated small subunits. So this small unit, so you will try to identify, well, not you, but the scientists will try to identify the smallest thing and put an N. And we don't know exactly what's N. We can define it with different characteristics and technique, but it's not really the point here in this lecture. And this is the definition of polymer. So just a very long chain made of organic material. And as I said, it's going to be hydrocarbon molecules, so made of carbon and hydrogen. And doesn't mean that you don't have anything else. So you can have, for instance, oxygen, nitrogen, or even fluorine inside. It's going to considerably modify the property of the polymer. At the beginning, we really use a lot of carbon and hydrogen polymer because it's all we discovered by making. It's quite a new science as compared to the concrete, which was in the 19th century. Polymers like 1950. So we still have a lot of things to discover about this material. And then, depending on how these chains are linked together, we have different names for that. So for instance, if you have only linear chain together, we are going to call that linear. Sometimes it's cross-linked, making like increasing the strength between the bonds. It can be branched, that means some chains which are exactly the same but are going to react and making side chains, modifying also the property. Or you have very, very dense 3D network. And all of this will affect a lot the property. As I said, the microstructure have a very, very, very important effect on the final property. So why are we using a polymer in general, not just for as a building material? Actually, for a lot of things. Because when we have discovered this material, at the time where aluminum, for instance, was a very conventional material for light material, because aluminum has very nice property. We discover polymer and we suddenly replace everything with polymer because it has a very low density, much lower than metal, because we are talking about a density close to 1.5 gram per square centimeter, which is like 3-5 times lower than metals. Not aluminum, but from steel, it's 4 times lower. It's pretty resistant to water, most of them, because of course, depending on what polymer you have, sometimes it's not resistant, but sometimes it is. But most of the time, it's not only resistant, but it's water repellent. For instance, the surface of this table is made of polymer. If I put some water on it, it's not going to absorb, it just stays on the surface. That's why we are making a lot of objects in the nowadays life to just life, because it has a pretty good short-term resistance to water. It has a high thermal and electrical insulation, which is quite important, especially from the electrical point of view, because everything which is connected to electric cable, electronics, it's made of plastic material because of this property. And we can shape it pretty easily. We are going to discuss about the processing later in this lecture. It's extremely easy to make shape out of polymers. We have a lot of different techniques, and as compared to metal, that you need to heat that up at more than 6, 7, 1,000 degrees using very complex machine. Here it's quite easy. You just melt it. You have the right mold. Boom! You have your pieces. You can make it very, very fast and have a fast production line. So that's very interesting. The creep deformation, it's something quite specific about polymer. We're going to discuss about it later. Low maintenance cost, it's a cheap material. So of course, if it's cheap, it's easier to replace. You have a problem, boom, you are replacing the pieces by something new. And for most of the polymer, you can just remelt it and make something else. So the recycling is quite easy. And it has a low durability. So as I said, it's resistant to water. So the water is not going to be absorbed inside the material. but if you use it outside, the polymer is not very resistant for different things, especially because of the UV light, because of the water, the rain, the degradation in general. But we are going to discuss that in one of the last slides of the course. So a lot of good applications. We ship actually to a lot of different products. I'm not going to spend too much time because we have like million examples of applications. So for instance, just some polymers very famous. The polystyrene, you all know the polystyrene, which is used, for instance, probably the panels here in the room are like polystyrene for insulation. It's probably useless actually because it's not the whole room, but anyway. But also for packaging application because it's really tough. So it's going to absorb the shock and the crack propagation. So it's going to protect your parcel for Christmas gifts. Nylon, just look, our clothes are like made of 50, 60, 70% of nylon. Extremely resistant and tough fiber, which is used for like 50, 60 years to make cheap and resistant clothes. Cellulose, so natural polymer, already discussed about that. So, which is made to make paper, tissues. Wood is made of cellulose, but we have a lot of practical applications for cellulose. And epoxy, which is a much more resistant polymer. We can use it a lot to make a composite applications. So for instance here, it's not just polymer, it's epoxy plus carbon fiber, which will make very resistant and tough material. Carbon fiber and epoxy are made for Formula One cars, spaceships. So it's very for high class application, but you can replace the carbon fiber with a lot of different fibers to also make cheaper objects, which are going to be very resistant as well. And all of these different polymers are like set in 3 categories. The first one is the thermoplastic, which is all of the polystyrene, polyethylene, polypropylene, polyvinyl chloride, and most of the polymer that you actually use every day. The second one is the thermosetting polymers. Most of the time we are calling that thermoset polymer, which are like the resin, so the epoxy, the vinyl ester, the polyester, which are much more resistant and also more expensive. So we are using a little bit less the thermoset, especially in the everyday life. And the last class is the elastomer, which is a bit specific class because it's in between thermoplastic and thermoset. And it's all, I mean, the main one is the rubber, so the natural rubber, which is used to make the tires of your car, of your bicycle, for instance. So we have these 3 categories, and now my goal is going to try to teach you how to recognize these different materials from the property or the microstructure. And you will see it's not that hard. It's really well defined, and actually you cannot really make mistakes if you know the basic rule. So this is like a table showing the different polymers. You can see that the thermoplastics are much more common in life. Why? Because it's one of the first polymers that has been discovered, and it's really cheap to make, and we made a lot of different modifications. So as I said, and as I showed before, you have, for instance, the poly. So this is the polyethylene. So you have a ethylene molecule, and which is going to be repeated n times. If I just replace, for instance, one hydrogen by one chloride, for instance, I'm making the polyvinyl chloride, which is here. And this is exactly how they made polymer. They took a molecule, they changed a very small fragment of this molecule, and they tried to make the polymerization process, making a new kind of material. I can imagine how it was fascinating for the researcher in this period, because it was super easy to actually make something new. Most of the time, I guess, it was a complete failure, but from time to time, they actually found a very interesting material. So that we are still using right now, so that's quite something actually. From the microstructure, how we can define these different polymers. Actually, it's directly coming from the microstructure. That's why we have different names. First of all, the thermoplastics is the conventional polymer. So how we can see it is very long chains that are interconnected together. So you have these long chains with N, which is over, for instance, 10,000. And all of these chains are going to be completely mixed together randomly, making this big batch of long chain tangled together. For the thermoset polymer, you have something a bit similar, shorter chains. But prior to utilization, what we are going to do, we are going to add something else which will make this chain react, and we are going to make cross-link reaction between this chain, meaning that all of these chains are like just tangled together, and suddenly we are making and we are blocking the chain with these bridges, meaning that now it's completely blocked, it's really rigid, and we are making a 3D network because all of this reaction, here is just I have like, but you can imagine that you have also the, like, in the perspective that you have also reaction everywhere, making like a very strong 3D network. And the elastomers are like in between thermoplastic and thermoset. So we have very, very, very long chains, so almost 1 million repetitive units. And it's liquid. Because for instance, natural rubber, we are going to discuss about that later, it's a liquid. We are just extracting that from trees. And then since it's not usable because it's a liquid, we are adding cross-link chains, branching this chain together, and we are adding it until it's solidified, because of course it's getting more rigid, and more it's getting solid, and this is how we actually make tires and why we have different class of tires. Depending on how we are going to add cross-link, we are going to make much more rigid elastomer, and we can have even brittle elastomer if we are adding too much cross-link. So this slide, just to mark it, because this is very important. You really must know that. If there is one thing that you have to learn by heart, is this slide. The rest is going to be self-explanatory, because if you know that, you can probably understand everything else. Polymerization process, I'm not going to spend too much time because it's not a chemistry course, but just going to explain quickly how does it work. We have two very different ways to make polymers, thermoplastic and thermoset, even elastomer. With thermoplastic, we are making chains with a reaction named polymerization. So what's going to happen? We are going to take a molecule, so for instance a vinyl chloride, which is a gas itself, making a long chain. So this is like a poly addition, because we are going to add this and we are going to make a very long chain out of it. We can also make what we call a polycondensation. I'm not going to ask you to remember all of that. Just remember that the poly addition, we don't have any byproducts because it's just the addition of the same molecule and we are making a very long chain out of it. But with the polycondensation, we are formation the byproducts. So for instance here, for the formation of polyester, we are just eliminating water, for instance, of this reaction. But it can be something else. It can be a toxic liquid that are extracted from the process. So it's a first step of the comprehension of what's wrong with polymer. Because even in the process, we are using stuff, for instance, pollutant gases, or we are going to have a pollutant byproduct. Well, in this case, it's water, so it's not that bad. But still, the process is pretty complex, and it can lead to things that we want to avoid. With thermosets, it's a bit different. We are going to make what we call pre-polymer, which is going to be viscous short chains, we are going to call it resin. Something you probably know, this resin is like a gluish liquid. And we are going to add something which is called a hardener, which are going to make this cross-link. So it's really a chemical reaction. We are adding two things together. It's going to react, it's going to solidify, and making this 3D network. Which is very important to remember in this case is that once the 3D network is made, it cannot be undone. This is completely irreversible, meaning that once it's like this, you cannot go back. And that also means that from the recycling point of view, it's really problematic because once you have this, the only way to break the chain is actually to destroy the material. So it can be either from mechanical cleavage or from thermal cleavage, so meaning that you are destroying your material and you cannot reuse it. With thermoplastics, this reaction can happen forever. You take this, you just remelt it, and you do it again. So that's pretty simple. But with thermoset, once you have the 3D network, it's over. You have your material, it's like this, and it cannot be changed. Thermoplastics, different kind of example. It's more or less the same slide that what I've shown before. Depending on how it's going to be branched, depending on what you are going to have as a side chain. So, for instance, replacing the hydrogen by a phenyl or by a fluoride, you are going to have very different properties. And I'm just insisting about the very different properties. You can have a material which is made to make, for instance, the plastic bag that you have in the shop to go to groceries, or you can have something which is used to make a stage sheet. It's really depending on the process and what you use here. You probably know this one, PTFE, but not with this name. It's with another name, which is the Teflon, which is used, for instance, for the frying pans for the anti-adhesive property. And the story of the Teflon is quite fun, actually. It was a big American company in the 50s, DuPont in the US, you probably know it. It's a big chemical engineering society. And the engineer made a mistake, actually. He was making another polymer. It was the Friday evening. It was quite, I think, he wanted to be in the weekend, I guess. And he made a mistake, and he hadn't realized that. And it's when he went back to the office on Monday that he realized that he put the wrong thing into his reactant. He was going to throw that away, and then he realized that the liquid was actually interesting. And what he did is actually adding fluorine in the mix, and he was going to add something else, I don't know exactly what. And he made by mistake the Teflon, which is patent, which was patented right after he made a mistake, and lead to billion and billion of dollars of this company, for this company, because this is probably one of the most interesting polymer, because it's completely anti-adhesive. The surface of the material, because of the fluorine, made absolutely no interaction with anything. So that means everything is going just to slip at the surface. That's why we are adding that to the frying pan, for instance. And it's very resistant, has a very high thermal insulation. So it's very expensive, but has a lot of properties. So I don't know what's the conclusion of that. Make mistakes and don't throw that away, but take notes, make patents. I don't know, but this is interesting. And then you have a lot of different things about this polymer, depending on the crystallinity, or you can make eco and friendly material, or green with the green chemistry, making a biopolymer like PLA, polylactic acid, or PCL, polycaprolactam, which are made actually not from petrosource based as polyethylene, but from natural thing. So the PLA is made from lactic acid, so it's from the milk, for instance, and the PCL, polycaprolactam, is made with something similar. So we are using byproducts from, for instance, the food industry to make polymers, which is quite common in the last 10 years. A lot of things are developed with it. Thermoset polymers. I was talking about you are adding a pre-polymer, adding a hardener, something else. You have a reaction and then a 3D network. I just explained you the functionality and how glue work. I guess that you know the epoxy glue. I mean, it's not something quite common, and it's exactly what's going on. You are adding the polymer, which is the epoxy, and then you are adding the hardener, which are going to react. And then, depending on which kind of polymer, depending on which kind of hardener you are using, it's going to be faster or slower, or more or less reactive. And then you are making a very strong 3D network. And this 3D network is actually going to react with the two surfaces of the thing that you want to glue. and it's trapped into the 3D network, and that's how the glue is working. It's actually trapping two surfaces in between of the glue layer, forming this very strong adhesive property. It's very interesting. Probably the main use of thermoset polymer are to make glues, but they have also other property. First of all, it's really resistant because of this 3D network. It leads to a lot of different property. It has better mechanical property, better thermal property as well. So that's why for applications where thermoplastic are a little bit soft, we can use thermosets for these kind of applications. The aesthetic is better. That's why we are using that as a finish and as a coating. We're discussing that with some students about different applications of polymers. It's soft, so that it's not rough as mineral material. So it can be easily used for interior applications, for instance. It's cost effective because even though it's slightly more expensive than thermoplastics, it's still much cheaper than metals and even concrete and mineral material in general. But it has a lot of drawback. Cannot be recycled, cannot be remolded, cannot be reshaped. This is the huge drawback of the thermoset polymer, is that once you are making something out of it, it's over. You cannot reuse it, you cannot even recycle it. So you know that when you are working about something, you have to landfill it after a while. Because right now we don't have any solution to recycle the thermoset. When I was in Canada, I was working with a company making, well, of course it's Canada, so it's a hockey stick, to play hockey. And it was made of, I'm not joking, I really had this project with a company there. It's really a cliche, I know, but they were using that because they made carbon fiber epoxy hockey stick. And the carbon fiber is extremely expensive. So when the stick was disposed, they wanted to recycle it. But since it was used with epoxy polymer, they had no idea how to do it. So what we did is we actually grind this, and we were using it as a filler in a new material because we knew that it was 50-50 carbon fiber and epoxy. In this 50, we would have an epoxy powder with no mechanical strength, but the other 50 would be very short carbon fiber with a lot, like very high mechanical property. So right now, the only solution that we have is actually to grind it and trying to replace it at a small level in other material, but it's not very good. So this is the main disadvantages, but also it's really toxic because the polymer itself is usually toxic. I don't know if you have ever heard about the bisphenol B, which is a very toxic chemical used for thermoset polymer. I don't know in your different country, but in France, 15 years ago, I think, they realized that they had a lot of bisphenol B into children plastic toys. And it was a new scandal because this was considered at that moment as irritant material, even toxic material. So they removed everything made of bisphenol B. But if the toy of your children are not made of this kind of polymer, everything else is made of it because it brings a lot of thermal stability and mechanical stability into the material. And the other problem is that the hardener itself is also full of very, very bad and toxic chemical because it leads to a very dangerous reaction, even though for glue it's at a very small scale, so that doesn't matter. But when you are making a boat out of it, just make your mask because it can be very problematic. And then the last class is elastomer. Already discussed about that. So at the beginning it's very, very long chain, which are directly extracted from trees. So it's rubber. So it's this white liquid extracted from tree. It has interesting property, but it's not solid. It's viscous. It's a liquid, highly extensible. It's very, very long chain. And then the idea that we had is we are going to make cross-link by itself with a process which is called a vulcanization. So it's addition of sulfur, so sulfur which is not very good for the environment as well, making this bonds made of sulfur, and we are going to increase the amount of cross-link chains depending on the application. So for instance, at the beginning we have 0 bonds, we have a viscous liquid. Then we are increasing like 1% of the polymers made of cross-linked chain becomes, for instance, these elastic bands that we are using to, I don't know why we are using elastic band nowadays, but to put things together, I guess, and which becomes a very deformable material. And then we can even increase the amount of chains. It becomes tires. Why tires are black? It's because of the vulcanization. It will change the color from white to black, and then we can even increase. So I don't know anything about Formula One, but I know that they are using different kind of tires, and depending on the amount of sulfur in it, it's going to change the softness, the hardness of the tires. And this is also why you should never burn tires, because when you burn tires, you are actually breaking these bonds and you are releasing toxic sulfur gases. So if you want a cheap way to die, you just have to just burn tires, and this work. No, just don't do that. But it's a common problem of polymer. It's because the polymer itself is made of carbon and hydrogen. So theoretically, when it burns, it should lead to gases not too toxic, even though it's a bit toxic. But it's all the additive that we're adding in it that will bring a lot of toxic gases when it will be burned. And I think the rubber is the easiest example to understand because of the sulfur here. So now you have all the knowledge about these different materials. I can go a little bit more in detail about the different structure. So for instance, why we have polymer like that? So how does it work? We have very long chains, and these chains, so I don't know if you have ever heard about the weak interaction in material. When things are very close to each other, we have what we call the van der Waals forces. It's a weak interaction, meaning that these chains, the chemicals, are going to be very close to each other. There is a very, very conventional and clear example of weak forces. I don't know if you know it. It's something that we all have in our body, for instance. The water is actually a lot of weak interaction between the hydrogen and the oxygen, because the oxygen will absorb electron and the hydrogen is going to give electron. This is high school chemistry. It's just a small reminder. And this is why actually the water and the ice has a very, very low melting temperature, because it's all about energy, and it's just at 0 degrees that we're actually breaking this and making the water liquid, because this interaction is so weak it's very easy to break. It's exactly the same with polymer. All of these long chains are interconnected with weak interaction. It's not the case with thermoset polymer, because with thermoset we are making the fluid network, and these weak bonds are actually interconnected together, meaning that it doesn't need a lot of energy to actually breaking these bonds. It's a lot of energy to actually break a bond like this, but the chains are so long that just to entangle the bonds, it doesn't need a lot of energy. I will show you. I have a slide there. So two kinds of bonds: covalent bonds between the molecules here, and weak bond between the chains. And you can make a lot of difference. And as I said, this science, like 60 years ago, was quite interesting, because we could make anything. It was just trial and error. We just put, for instance, the polymerization is just putting polymer together. So we have two polymers, we are mixing it together, and we are making that. This is an example of the SDS, the polystyrene butadiene styrene. So it's polystyrene and another polymer mixing together to actually make something new. And of course, all the time you have new properties. The crystallinity of the polymer, we already discussed about the amorphous phases, the crystalline phases. I don't know if you remember when we were talking about cements, about the CSH gels, which was amorphous. In polymer, something which is very interesting, especially in thermoset polymer, is that we have polymer which are amorphous and crystalline. The amorphous polymer means that the chains are completely random. The chains are so long it's so complex that it's very, very hard to have something which is crystalline, which has a very defined order. But depending on how you are cooling your material, if you give time for the chains to actually make some order, you can have crystalline polymers. And this is very interesting because polymers are among the only material in the world that can be both crystalline and polymer. That means a part of your polymer is going to be completely random like this, and a part is going to be very defined. And a material, a polymer, is actually never completely amorphous or completely crystalline. It's always like in a grayscale. It's sometimes it's 80%, 20%, and depending on the crystallinity, it will affect significantly all the properties, thermal property, crystallinity, and everything. Of course, the elastomer and the thermoset cannot be amorphous, crystalline, sorry. Why? For the elastomer, the chains are too long. It's so long that it cannot be, you cannot reach, even with the slowest cooling rate when you are making it, it's not possible to make an order because it's so big that it's too complex. With the thermoset, why? It's because the chains are like in random order, and then you are making a 3D network, and the reaction is random. And if you had any randomness in the reaction, you cannot make something crystalline. It has to be clearly defined by a chemical reaction, for instance. So thermoplastics are amorphous and crystalline, and thermosets and elastomer are only amorphous. This is complicated, so I'm just asking you a little bit of attention on this slide. This is the most complicated slide of today. I don't know if I'm going to ask you for the final exam, so you can even like sleep if you want, but it's very important information about polymers and about how does it work. It's not a conventional material. Because you have crystallinity, because you have amorphous parts, it acts differently as conventional material. A metal, for instance, you have very defined states. It's liquid or it's solid. You don't have something in between. It's a solid. You reach the melting temperature, it becomes liquid. That's it, that's all. For the polymer, it's slightly different. Because you have amorphous parts and crystalline parts, it's going to react differently. That means the crystalline part will act exactly as a metal, because a metal is actually a crystalline material. So you have a melting temperature, it's liquid, it's solid. It's what happened here, for instance, when the material is liquid at high temperature, and then I follow this to actually a cooling, imagine a cooling rate. So I'm increasing the temperature, everything is liquid, and then I'm decreasing the temperature. If my material is 100% crystalline, it's liquid, it's solid, acting like a metal. But it becomes more interesting and complicated actually when it's also amorphous, because amorphous materials such as glass doesn't have only a melting temperature. When you will reach this, you will have an amorphous solid. It's actually something which is very viscous, because polymers are something which we call viscoelastic and viscoplastic. It can be deformed. You have a movement of chain under stress. That means if your material is like this and you put any stress on it, so you just put it on the table, nothing will react. But if you start to actually pull it, the chain together are still not exactly ordered like crystalline solids, so you cannot really move the chain because here nothing can move. But with the amorphous solids, since the chains are all together and can slip together, you still have some movement. And then you have a temperature here which is called the glass transition temperature, which is the difference between amorphous material when they are amorphous solid and a glassy solid. And when it's a glassy solid, it's exactly as glass. It doesn't move. You have a very, very slight movement of chain. A very good example is glass. Glass is actually a mineral polymer because it's a polymer made of silicon oxide, making a long chain of silicon oxide. And you probably won't believe me, but actually a glass material, conventional glass, is never actually solid. It's just at a glassy state. And you still have a small deformation over time of glass. That means if you have a glass, if you look very precisely with a microscope, you will see a very, very, very like slow deformation of glass. And if you don't believe me, a very good way to do it, to check it, is go to a very old church using glass that is like 300, 400 years old, and you will notice, it's not very easy to see, but you can notice that the glass is actually, with the gravity, the chain are going to the bottom of the glass. It takes hundreds of years to do that. It's a very small differences, so I'm exaggerating a little bit. But the glass chain, as the polymer in the amorphous, can still move slowly. And it's exactly what's going on when I'm increasing the temperature. Is that when I'm reaching this glass transition temperature, I'm actually activating the polymer, and then the chain can move together very easily. And then I'm reaching the melting temperature where the chain are completely exploded. Like you don't have any order or any interaction. I'm actually breaking all the interaction. And regardless if the polymer is amorphous or crystalline, you will have a movement. So, quite complicated, but usually this can be just a program by itself, polymer chemistry. So I'm trying to put everything in 45 minutes. It's not easy. This glass transition temperature is extremely important because when you are going to reach it, you are going to considerably modifying the property of the material. You are reaching a TG, it's going to be very soft. So this is what I'm calling thermal stability of the material. We usually don't talk about the melting temperature because melting temperature is too late. You are melting a material. But the glass temperature, sometimes you don't really notice it, but everything becomes soft and can be problematic, especially for building applications. How you can change the TG temperature glass, so glass transition temperature. You can add different things into the polymer. It's all about the movement of the chain. So if I'm adding, for instance, particles that are interlock the chain together, you are increasing the TG because the movement of the chain is limited. You can change the length of the molecule. If I decrease the size of the molecule, of course, it's going to be different. The TG is going to be different because the mobility is going to be easier, for instance, or limited. You maybe increase the crystallinity of the material. So the crystallinity, yeah. So you have a lot of different things, and I just invite you to have a look to handbook or different description of polymers. I think I have a small table here showing the TG and the melting temperature of polymer. And what is very interesting to see is that actually the TG of the material are very, very, very low. For instance, for the natural rubber, it's like minus 75. That means at room temperature, the material acts actually as a viscous material. And it's normal because, as I said, when it's extracted from tree, it's already liquid because we have already reached the TG. For some material, the TG is much higher. I think a good example is the polystyrene. It's 100 degrees. Hi, good morning. And you don't really have the melting temperature because when you are reaching the TG, the material is already completely deformed. And since it's a very and fully amorphous material, there is not a lot of differences between the melting temperature and the glass transition temperature. So keep a small reminder of this table. You can have a look. Quite important. Mechanical property. So we are reaching the end of the different properties of the material. This one is probably easier for you because it's not about chemistry. Quite simple. Thermoset polymer, stiff and resistant, but not ductile at all. So that means it's a fragile material. Why? Because we are making a 3D network. There is not any possibility for the chain to move. That means once you are reaching the ultimate strength of the material, you are breaking it because you are breaking the chain. The thermoplastics, you have very long chain that can interact together, meaning that we have a very, very, very ductile material, and I'm just stretching about the very ductile material. It's up to 1,000%. Just to give you a comparison, aluminum or steel, we are talking about 50, 60, 70%. Here it's 1,000, more than 10 times its own length. And you know it. You already play with a rubber band, for instance. You know that you can increase the length of the polymer like a lot. It's even higher with the elastomer, as I was talking about rubber bands. But you can see also that the strength is really decreased. thermoset polymer has a strength which is acceptable, but when we are talking about thermoset and even elastomer, especially elastomer, we are like below 1 megapascal. To give you a comparison, steel is 400, 500 megapascal. So that's it's up to 500 times. So that's why it's really best for non-structural applications. But when we want to use it for structural application, we have to be smart about it. So how the polymer deformation with my awesome skill in MS Paint shown in the screen. It's actually quite simple. You have a very long chain, and when you want to pull on this chain, yes, a question?
For the former slide, I was
Yes.
wondering how the characteristics of those three
Yes.
types of
Yeah.
polymers change in the temperature.
Yes. I have another slide later, so I'm going to come back like that. But the temperature is really affecting the polymers, and I can have a small discussion about that right now. Temperature is affecting all the material. Temperature is affecting the steel, temperature is affecting the concrete, but with polymer is like 10, 100 times more affected. Because with the other materials, the difference is like 1-2% of the final property. The polymer can double or triple the property. Why? Because the chain, the mobility of the chain, everything is explained with the mobility of the chain. You increase the temperature, you increase the mobility of the chain because temperature is just atomic movements, and then it's easier to be deformed, so you increase the ductility, but you decrease the resistance. Just as easy as that. And with this, it's exactly like that. You have a lot of chain, and you start to pull on this chain. The first thing that you do is actually you untangle the chain together, because it's such a mess. Like you have a lot of, like a rope, you know, like you want to get a rope to do rope climbing, for instance. Everything is tangled, and you try to start to untangle it, and you know, like it never ends. You know, like you don't know how to do it. And at the beginning, it's very easy to do it because, of course, it's so entangled that it's very easy. That's why you need a very low strength to actually untangle this polymer and to pull on this polymer. At some point, you will reach a state that everything is entangled, and you are starting to reach the maximum length of your chain. That means at that moment, when you continue to stretch it, you break the chain. So this is the deformation. The ultimate deformation is at the final length. You increase actually the length, which is actually the utility of the material, but you cannot do that forever. So at some point, you have the maximum chain, and you will break it if you increase a little bit. And this is the ultimate tensile strength. And of course, the cross-linked polymer are stiff and cannot be elongated because it's like you have your rope for rope climbing, but it's just attached with some small clip. I don't know what you would do that, but it's you cannot really untangle it. So just remind that with the chain mobility. Thermal property. The slide is here. You can see the difference at very low temperature. So for instance, close to 0 degrees and close to 60 degrees, the mechanical property completely changed. We have something which is called the ductility fragility temperature zone. Plastic at some points will act as a brittle material. For instance, here at 4 degrees it happens. Why? Because the chain, when the temperature is very low, they don't have the time to actually untangle and like deform. That means it will break directly because it doesn't have the time, so you actually break directly this. So the strength needed to break it is much higher. You increase it from like almost 8 times, but the material is not really ductile. And usually, since we are using a ductile material, polymer as ductile material, very good example is snow shovel. You know, to remove the snow from your place. Still in Canada, middle of the winter, minus 35, extremely cold. If you have a shovel which is made of polymer, it will break. Because it's so cold that you actually have a polymer which is like this. So you will do it one time, you will do it second time, small deformation, crack, it's over. But if you want to remove snow at 60 degrees, no problem, because here it's a very ductile material. Of course, it's going to be less rigid, but and you have to find snow at 60 degrees, which is not very easy. Polymer can be transparent, very important. We will talk about that when it's going to be different applications. But what affects a lot the transparency is the crystallinity. Depending on if it's amorphous or crystalline, you will change the transparency of a material. For instance, good example is the polycarbonate, which can be crystalline or amorphous. In this case, it's amorphous, it's transparent. But the crystalline polycarbonate is more resistant, but it's not transparent. So you have it's absolutely useless to use it. Different process of plastic. We are going to finish the first part of the lecture on this. You can add a lot of things. This is, I think, one of the main advantages of the polymer. It's very easy to process, and it's very easy to modify. You have a polymer, you want to make it red, boom, you add the red dye and it's red. You want to make it blue, boom, it's blue. You want to make it more resistant, okay, I'm adding some filler. You want to make it like fire resistance, you add something. You can add a lot of different things. You have millions of examples out there making different class of material, more resistant, less resistant, more ductile, red, transparent, water repellent. So it's quite easy to do it. You just have to mix two things together, making like a reaction, and you will modify your polymer. So different kind of processing. I have a video showing it, so I'm going to go pretty fast. You have, for instance, the injection molding. So injection molding is, well, and you know what? I have a video here, so this is the description. I should put that here. I'm going to show you this, and then we can discuss.
Hi, I'm Dr. Karen Helper from the Akron Global Polymer Academy. And today I'd like to introduce you to the world of polymer processing. If you take a look around your house, you'll find numerous items made out of plastic. Have you ever wondered how some of these were made? Well, today we're going to answer that question by taking a closer look at how 3 common plastic items are made.
You know that you ask yourself the question very often. Oh, polymer made this.
Let's begin with our jump rope. The plastic rope part was made by a process called extrusion. The extrusion process is similar to what happens in a Play-Doh fun factory.
It's a very good example,
Materials
actually.
chamber and pressed
It's
out
not
through a
more
mold,
complex than that.
which is also called a die. The shape of this mold or die determines the shape of the finished product. The machine behind me is called an extruder. Instead of using Play-Doh, it processes plastic pellets like these. Sometimes another substance is added called a filler.
So this is thermoplastic, which is made under pellets. So this is the
This
industrial
process
way
begins
to do
by
it.
placing the pellets and filler into a feeder, which leads to a hopper. From here, the materials enter a heated barrel, where they are melted. A screw rotates the side of the barrel and pushes the melted polymer out. It also helps mix the melted polymer for consistency. The polymer exits the extruder through a die, which determines its final shape. Just like the Play-Doh Fun Factory, different dies can be used to make different shapes of materials for different products. The extruded material is then moved along the conveyor belt, where it cools. Since most polymers are insulators and maintain heat, it's important to allow the material enough time to cool.
And they said the crystallinity will be affected by the cooling rate. So always cool down is very important.
Water may be used to help cool the material. Fibers can be formed by taking an extruded strand and pulling it before it is completely cooled. This action stretches the material and decreases its diameter. These thin fibers can be used to make items like clothes. And that's how the extrusion process works. Now, let's take a look at how coasters are made.
Injection molding. I think the previous one and this one are the most important ones.
This is an injection molding machine. It actually has an extruder built right into it, and that's exactly where this process begins. The extruder melts and mixes our polymer pellets and additives. Next, the machine injects a small amount of the melted material from the extruder into a closed mold cavity. This mold contains the actual shape of the final product. The entire mold is then cooled down until the part is able to maintain its shape. When it's ready, the mold opens and the product drops out. This process continues until the desired amount of molded products are made, and
The
that's
process
the
is
injection
extremely
molding
fast.
process.
Once you have a design mold, you can do it forever. So that's why it's extremely easy to shape materials.
Have you seen one of these? It's called a floonie. And it gives you a picture of what happens during our next process, which takes melted plastic and blows it into a thin film. The film blowing process also begins by using an extruder to melt and mix a polymer. Next, the melted material is pumped upwards through a circular die. Air is also blown into the polymer, which causes it to blow up like a balloon. This shapes the material into a thin film. A larger film can be created by increasing the air's flow rate. The film cools as it continues to move upward. At the top of the machine is an element called a nip. This is used to press the blown film together, making it flat so it can be rolled up. The rolled up film can then be cut up and used to make products like this plastic bag, and that's the film blowing process. And that concludes our brief introduction to the world of polymer processing. The next time you see one of these common plastic items, you can say, I know how that was made.
You know it now. Okay, so like what's important to remember on that, I think the injection molding and the extruding is very important. The extruding is here to mix this pellet together. So it's extremely important with what I said before. You can do whatever you want. Why? Because the polymer is very easy to melt. To go to 100 degrees is enough. And then you can mix anything together. You are going to make a new polymer, making new pellets that you can use, for instance, in injection molding. About the other examples, you have the electrospinning process, which is a bit the same. You are like just injecting something, it will solidify very, very fast, and then you are making the polymer. Extrusion, you know it now. Calendering is the third one that we see in injection molding. So you know everything now. So let's make a break, and then we are going to talk about small applications and applied. So now you know everything. That's good. That's done. So yeah, make a 10-minute, 15-minute break, and let's see each other after that.